Okay, the carbonic acid bicarbonate buffer. Now this is one of many presentations on this buffer system. Go on YouTube and probably find hundreds of very well presented explanations of the carbonic acid bicarbonate buffer system. This, as I presented, is from a chemistry standpoint, strictly academic. It does not pretend to offer any medical advice one way or the other. To understand the carbonic acid buffer system, first thing we need to do is look at the chemical reactions that are involved with the I would like to begin with the molecule of carbonic acid and talk a moment about its character. The molecule is a weak acid and is a diprotic ionization character and follows a process of losing one of the hydrogens and then a second hydrogen. More specifically, if we look at the carbonic acid ionization, we find that H2CO3 in an aqueous or medium will ionize to give hydronium ions represented by H plus HCO3, the bicarbonate ion, also in aqueous solution. The first ionization step, Ka1, is 4.3 times 10 to the minus 7. To the minus 7. The second ionization is HCO3, which undergoes ionization to deliver additional hydronium ions plus CO3 to minus aqueous, and Ka2 3.5 times 10 to the minus 11. Now, it is generally accepted that if a compound has or two acids have the larger Ka value, will deliver most of the hydronium ion into solution. The one that has a smaller Ka value indicates that the second hydrogen is held on with a strong bond and is very difficult to ionize. So in the carbonic acid bicarbonate buffer system, it is generally accepted and assumed that all of the acid that is delivered into the system, it comes from the carbonic acid first ionization step. Now, carbonic acid also has the ability to break down into CO2, carbon dioxide, and water. Is one of the molecules that we look at in double replacement reactions in which an acid and, say, sodium bicarbonate are added together, and we see a lot of bubbling and effervescence. Alka-Seltzer dropped into water, that's giving off CO2. And so in a second capacity, H H2CO3, if heated, or it's very, very unstable in terms of its structure, in that it will break down, decompose into CO2 gas and water, as shown here, with a moderate amount of heat input. You can observe this by taking something like baking soda plus some vinegar, okay, and add these two together, and what you're doing is putting sodium bicarbonate, the baking soda, in with acetic acid. This is the ionizable hydrogen here, and we will be producing carbonic acid, which continues, and of course a sodium acetate salt. Sorry. But the carbonic acid, which picks up the carbonate hydrogen bond, this is a reasonably strong conjugate base, and will attract the hydrogen into the carbonate structure. I'll show you that in a minute. And when it does, it will continue to break down into CO2 gas and some additional water in this system. So we have carbon dioxide, and water. A good example is an Alka-Seltzer dropped into water. That's an weak acid working with a salt, conjugate base, citric acid, sodium citrate, and generating carbonic acid again, and that decomposes, gives CO2, which comes out of the system as a gas, and of course water would blend in with other water, say as a solvent. And now the purpose of the bicarbonate carbonic acid buffer system is simply to prevent radical changes in the pH of the blood when stress factors occur that would disturb the stability of the buffer equilibrium. Now, to understand how the buffer system functions, you really need an academic background in these topics that I'm showing here. You need to have an understanding of acid-base chemistry, that is, what we mean by acidity, what we mean by basicity or alkalinity, and we can interchange that, and what we mean by pH. You also need to understand how buffer systems are prepared, their general composition, and how a buffer system functions. The buffer system functions based on a process known as common ion effect. Which, by textbook definition, common ion functions to decrease the extent of reaction or ionization of the carbonic acid, and retard it if its common ion is present. We'll say more later. And you certainly need some degree of understanding of acid-base equilibrium and how it functions relative to being described, or how it's described by Le Chatelier's principle. Le Chatelier's principle says that if a stress is applied to a chemical equilibrium or a system in equilibrium, that equilibrium will shift away from the applied stress and establish a new equilibrium. Now, in a fundamental way, that's exactly what the carbonic acid bicarbonate process is doing. When a stress is applied for external, environmental, physiological, biological, however you wish to define the stress, any stress factor that would disturb the stability of the bicarbonate, carbonic acid equilibrium, the system inherently takes over and adjusts itself away to compensate for the applied stress. So let's begin with a discussion, a presentation of acidity, basicity, alkalinity, and pH. What's an acid? Well, it can be described in one of three ways. We'll use the Arrhenius method first. An acid is an electrolyte that, when dissolved into water solvent, ionizes and increases the hydronium ion concentration. Okay, HCl in water is hydrochloric acid. It contains an ionizable hydrogen. That is, the hydrogen will break away from the chloride in the structure very easily or in water, and it will react with a water molecule. Now, water has what we call an electron pair on it, which gives it a negative character, and the hydrogen, without its electrons, nothing but a proton, is transferred over to the electron pair on the water, generating a structure. It's a little bit like this. It's not triangular, pyramidal more than anything. But when the hydrogen attaches, it takes on a cationic charge. This is the hydronium ion. And it's usually written H2CO3 plus. Now, to save time and effort and energy, we equate this to just saying, well, it's delivering hydrogens into the solution, but in reality, a proton doesn't float around by itself in an aqueous solution. It attaches to water and forms a hydronium ion. Well, also, you don't want to forget about the chloride, just aqueous, hydrated in solution also. Using the condensed or abbreviated notation, we'll just simply say HCl in water will ionize to deliver an increase in hydronium ions, H+, plus the halogen anion, chloride, and represented in that capacity. And so any compound which, when placed into water, ionizes and increases the concentration of the hydronium ion or hydrogen ion is considered to be an acid. Now that's an Arrhenius definition. Another definition of an acid is a compound which, when placed into water, functions to deliver or act as a proton donor. And such as this I've shown originally. So HCl placed into water donates its proton to water molecule forming the hydronium ion. So this would be the acid, and that would be what is referred to as the base. Now that's the Bronsted-Lowry theory. And here we have a conjugate acid by terminology, and there's a conjugate base of the acid, and this is a conjugate acid of that base. So proton transfer is one theory, and ion delivery into the solution is another. Now there's another theory known as the Lewis theory, which is based upon the idea of electron pair donation and positive centers for receiving electron pairs. And so the acid-base theory could be applied that way. It doesn't matter which theory you use as long as it serves the purpose of defining what you're doing. I like to use the Arrhenius theory in the case of describing acidity and basicity. It's just less cumbersome. Now, I will integrate the Bronsted-Lowry theory into this when it's appropriate, but I don't use very much of the Lewis theory to explain the nature of the bicarb carbonic acid equilibrium. Now, a base is defined pretty much in the same way as an acid. A base is an electrolyte, which, when dissolved in water, undergoes ionization and increases the hydroxide ion concentration. The nature of acids and bases as electrolytes it comes from their ability, when dissolved, ionizing, it comes from their ability to conduct an electric charge. So hence the electricity electrolyte issue comes into the definition. But nevertheless, the ionization of sodium hydroxide increases the hydroxide concentration in this process of ionization. Now this symbology describes the behavior of a base or the nature of a base in terms of the Arrhenius theory. And the acid is an electrolyte that increases hydronium ion concentration. That is, gives H pluses, and a base ionizes to increase the hydroxide ion concentration. Now, earlier I mentioned that the process could also be described by what is known as a Bronsted-Lowry proton transfer process. In which a ionizable hydrogen is donated to a compound which has a relatively large negative character and would absorb or bond with the proton being delivered from the acid. Okay, I'll use the carbonic acid as an example of the Bronsted Lowry theory. If you have carbonic acid H2CO3 and you put it into water, one of the hydrogens here is ionizable. Both of them are ionizable, but the second one is less ionizable than the first one, which is another story. And the first hydrogen, if you will, the first ionization, delivers a hydrogen to the electron pair, which has a high negative character, and produces the hydronium ion, H3O, with a plus, and leaves us with HCO3, the bicarbonate ion, like that. And this process, this would be the acid, and the water in itself would be the base by the Bronsted-Lowry theory. This, in general, is a proton. I'll write it out in a shorthand. This is a proton donor, and this is a proton acceptor. At times, it's wise to use the Bronsted-Lowry theory when talking about the carbonic acid equilibrium and how it functions. Now, in the world of chemistry, especially in analytical chemistry, we work with acids and bases extensively. It is prudent to use a designation for acids and a designation that represents a base in terms of what is known as the pH factor. pH is a relative measure of the hydronium or hydrogen ion concentration. pH, just as a sidebar, comes from a mathematical method known as p-factor analysis, whose purpose it is to place very small numbers in a more convenient form. That's all it's used for. So p-factor analysis converts hydronium ion concentration to that would be concentration to more convenient forms. Now, when you're working with acids in solution, you will normally, especially weak acids, you'll be working with concentrations that are very small. Okay, if we look at carbonic acid, say we take a 0.10 molar solution of carbonic acid, and the first ionization, Ka1, is 4.8 times 10 to the minus 7. You can calculate using the following equation the concentration of the hydronium ion in solution, which is the Ka value times the concentration of the acid, square root of that, and it'll give you the concentration in moles per liter, which is the most widely used designation for compound concentrations. So in this case, it would simply be the 4.8 times 10 to the minus 7 times 0.10, and that would be in moles per liter, giving 2.2 times 10 to the minus 4 mole per liter in hydronium ion. Well, that's a little cumbersome, and we could represent acids in that capacity if you wish, but if you want to use the pH factor, that's P factor, meaning factor is hydronium ion concentration. The pH factor is defined as minus log of the, in this case, whatever the factor is, in this case the hydronium ion concentration. So we substitute the 2.2 times 10 to the minus 4 mole per liter into the hydrogen ion concentration, and we get minus 3.7, which is, of course, minus times a minus is a plus, so that's 3.7. For pure carbonic acid dropped into water, 0.1 molar, you can expect a pH to be in the vicinity of 3.7 if you use the pH meter to measure the pH. Now, the analysis of aqueous bases revolves around the fact that the base is an electrolyte which, when put into water, delivers hydroxide ions. So when we make calculations of base concentrations, we want to calculate the hydroxide ion concentration. Well, essentially, if we take a weak base, ammonium hydroxide is classified as a weak base in aqueous solution. We find it to ionize to ammonium ions and hydroxide ions, like that. And to define the base, we need to find the hydroxide ion concentration. Well, you can use a formula that's very similar to the one we use for hydronium ion calculation, and provided we know what the Kb expression is, a value, it's well, in the same capacity, we're looking for hydroxide ion concentration, molar concentrations. And it can be defined in terms of Kb times the base concentration. In this case, let's take also 0.10 molar, like that. And so we're trying to find out what the hydroxide ion concentration in the ionization is. So this would be 1.8 times 10 to the minus 5 times 0.10, square root of that, and moles per liter, which gives us 0.0013 molar in hydroxide ion concentrations. Well, the problem is acidity, basicity is represented in terms of pH factor, not pOH. Well, we can still calculate a pOH, which is minus log of the hydroxide ion concentration, which is minus log of 0.0013 molar, giving us 2.87 pOH. Well, it can be shown that pH plus pOH always equals 14 at 25 degrees Celsius. So, and substituting 2.87 here and solving for pH, we have 14 minus 2.87, which gives us a pH of 11.1 for this ammonium hydroxide. So a moment ago we found that 0.1 molar carbonic acid in water theoretically would get at 25 degrees would give us 3.7 pH, and a 0.1 molar ammonium hydroxide 11.1. Well, how do we relate those to alkalinity, basicity, or acidity? Well, the pH scale has been defined relative to pure water. Some people derive it from autoionization of water. For pure water, at 25 degrees C, we find that autoionization of water results in delivering a certain quantity of hydronium ions and hydroxide ions into solution. Well, it's also been shown that the hydronium ion concentration at 25 degrees Celsius in pure water is 1 times 10 to the minus 7 mole per liter, as is the hydroxide ion concentration. They're equal. So if this breaks out, it's going to send one hydrogen and also one hydroxide. So these, of course, would be 25 degrees C, 1 times 10 to the minus 7 molar. Well, again, if we apply pH minus log hydronium ion concentration, we have minus log 10 to the minus 7, which is 7. So that's a balance between hydronium ions and hydroxide ions. You have just as many H's as you do OH's, and we call that a neutral condition. So we move away from that to a higher hydroxide than hydronium ion. We call it a basic solution. If we have a higher hydronium ion concentration than hydroxide ion concentration, we call it acidic. We can represent this on a simple number line and show that 7, if we represent neutral at 7, this is where the hydronium ion and hydroxide ions equal concentrations. If we move toward the extreme, 1 is low, 14 high, we find that from 7 to 14, the hydroxide ion concentration will be greater than the hydronium ion concentration. As a result, we call it, by convention, an alkaline system or basic system. And if we have a solution of hydronium and hydroxide ions whereby the hydronium ion is greater concentration than the hydroxide, we call it an acidic system. So that is the foundations you need for understanding the fundamentals of acidity. And we could get into some more complex issues, but I think that will suffice for right now. Okay, now let's talk about the chemistry of buffer systems. And again, what is a buffer system? Buffer systems function to prevent extreme changes in pH with addition of quantities of acid or base. Now, a buffer system is to be acid, it can be neutral, or it can be basic. Preparation of a buffer system depends on what pH you are trying to achieve. Now, the composition, textbook composition of a buffer system is a weak electrolyte and the salt of the weak electrolyte. And the capacity of the electrolytes being a weak acid and the salt of that weak acid, or a salt which would function as a common ion, now, the thing about this is that it is going to be carrying a conjugate base of the acid. We'll get to that. And a basic buffer would be, say, a weak base along with the salt of the base. So we could show you some examples. An acidic buffer would be something like acetic acid and sodium acetate, like that. Alkaline or basic buffer could be ammonium hydroxide and ammonium chloride in mix, showing in there. Now, when the composition contains the weak acid and the weak and salt of the weak acid, or weak base and salt of the weak base, the anion, if it's an acidic combination, will function to retard further ionization of the weak acid. And the salt of the weak base, the cation, will function to retard or limit the ionization of the weak base. So the effectiveness of a buffer system depends on the concentration of the conjugate base and the salt, if you will, and against the concentration of the acid as you change the concentration. Okay, to understand how a buffer system truly functions, and especially the carbonate bicarbonate system, you need to understand how the chemistry of a buffer system functions and what it does. And we'll start with a simple system. Buffer systems are based on what is called the common ion effect. Let's start with a 0.10 molar acetic acid, aqueous, and a 0.10 molar sodium acetate, aqueous, as our buffer system. Well, the nature of this is based upon a weak acid, acetic acid, in which the acetic acid in solution, aqueous solution, will ionize to deliver, to a certain extent, hydronium ions and the acetate ions. By itself, without any interference in the solvent, water, it will ionize in equal parts. You will have acetic acid delivering the same amount of hydronium ion and acetate ion. However, in a buffer system, you are adding a common ion. So these are the ions that are delivered from the acid, and you put some extra ion, as in the acetate ion, into the system. You are adding a common ion. So initially, concentration initially, we're starting with 0.10 molar acetic acid, and we are mixing it with a 0.10 molar sodium acetate, or OAC. This is just a spectator ion. It don't do nothing. We'll just leave it at that. Okay, now initially you just poured them together. It's kind of like a horse race. You got these items are in a starting gate, okay? And in the CI row right here, the initial row, we haven't let them react yet. Now open the gate and let the horses run. It's kind of an analogy. Well, before the horses leave the gate, we don't have any hydrogen here. It hasn't started ionizing. So essentially, we put a 0. Now, open the gates, let them run, and so what do we have? We have the concentrations changing. We go through the kinetics region of the equilibrium before we reach equilibrium. And the concentrate, as it shifts in delivering hydrogens, this, of course, will go down in concentration. And the hydronium ions will go up in concentration, as well as acetate ions in an equal amount. Okay? Now, it's common practice when you are working with electrolytes, weak acids, in this capacity, that their ionization is going to be extremely, extremely limited. And so the amount of X in here subtracted from the 0.1 essentially makes little or no difference in the amounts of acid and acetate compared to, this would be about 10 to the minus 5, 4, 3, whatever. And you subtract 10 to the minus 3, 4, 10 to the minus 5 from point, we still got 0.1. So we're going to drop this X and say 0.10 molar. And at equilibrium, we're going to have whatever X gives us, and we're going to have 0.10 molar. Now that's our equilibrium, our acid. Now, it is common knowledge that if you have equal salt concentrations and acid concentrations, the hydronium ion concentration right here, okay, X, hydronium ion concentration, will be equal to the Ka value. And in this case, 1.8 times 10 to the minus 5. And we can put a moles per liter on that. And so our little system has a hydronium ion of this. Now, what's the pH? Well, it's minus log hydronium ion concentration. Well, I better not use that. Let's use the H plus. Okay. That's minus log 1.8 times 10 to the minus 5. Okay, and so we have a pH of 4.74 after we mix the two together, if that's what our specified combination is. 0.1 molar salt, 0.1 molar and acid. Okay, now the idea is not to make buffer solutions. The idea is to use buffer solutions to prevent changes in pH. So as we prevent changes in pH, how do we do it? What has to happen to our equilibrium? Well, the chemistry of this equilibrium has to remove excess acids or excess base in the process of adjusting away from the applied stress. If you add excess hydronium ions, this chemistry equilibrium has to adjust itself to get rid of the extra hydronium ion. Or if we throw in hydroxide ions or extra base, the chemistry of this equilibrium has to remove the excess base. Okay. Well, one of the factors that affects a stable equilibrium is adding extra reagents into the equilibrium system. Throwing in some extra acid, or throwing in some extra even acetate, or throwing in some extra acetic acid. That's a concentration effect that places a stress on the equilibrium, the established equilibrium, and has to be adjusted by the chemistry. It does not have any help anywhere else. Now, the way I look at this is as the equilibrium. Let's assume this equilibrium is acting like kids on a seesaw, like this. Now, while the equilibrium is balanced and stable, we have the horizontal condition, or the configuration of the seesaw. However, if we bring in some extra acid or extra base, or throw in some more salt or acetic acid, that's like adding extra players to the seesaw. When one gets off, what's going to happen? Or we add more kids over here on this side versus this side, what's going to happen to the seesaw? It's going to tilt. So that's the disturbance. And so the system's no longer at equilibrium then. So let's just start with excess hydrogen. Let's say somebody brings in some excess hydrogen. So in this case, let's put it right over here. You're adding some excess H plus, throwing in some hydrochloric acid or something. Well, it's going to load up on this side of the seesaw. You're going to have an extra kid that looks like hydrogen ions sitting over here. Okay, well, this balance is not going to stay. So it's going to get heavier on the right side, so your seesaw is going to tilt like that. And so you're going to have a system that is no longer at equilibrium. Like this. Now you still have the same molecules. Minus. Right here. But the disturbance is over here. You had the excess. Now, according to Le Chatelier's principle, when a stress is applied to an equilibrium, the equilibrium will shift away from this stress to reestablish a new equilibrium. So what will happen here? Okay, hydrogen will have to combine with the OAC and make some more additional HOAC so that the left side of this diagram will get heavier and cause the seesaw to tilt back down. So the shift will be toward the HOAC, and left in this diagram. So hydrogen will combine with OAC, and it'll continue to combine with OAC until it takes out the excess, right there. And so and we'll go through Le Chatelier here, and then you establish a new equilibrium. Now, one thing that you need to understand is the concentrations of the acetic acid and the acetate are no longer equal. When we made our original, we were 0.10 molar, 0.10 molar. But when we added the extra hydronium ion, it disturbed the equilibrium, tilted right, so it has to shift left. And that causes the concentration of the available OAC to go down. And it'll continue to go down until you absorb enough of the excess hydrogen and create enough acetic acid, whose concentration is going up now, to reestablish the new equilibrium. So the OAC in the new equilibrium is higher. And the OAC in the new equilibrium is lower, in an amount equal to how much acid you had to take out of the system. Now, we'll apply that idea to a numerical quantitative evaluation of this in a few minutes. But first I want to do the other side of the equation. What if we add an excess of base? Here we had an excess of hydronium. When an excess of hydroxide is added into a stable equilibrium, it too will cause a stress factor. Okay? But it tilts the other way, huh? Okay. It tilts to the left. Why? Because hydronium ions or hydrogen ions will react with the excess hydroxide. That is, H plus will react with the OH and form water. Right there. And that capacity, as it does that, it will continue to do that until it removes all the excess hydroxide. So that's going to cause this side of the equilibrium to get lighter because you no longer have enough H's holding that end of the equilibrium down. And so you will see a tilt to the left, like this. And our equilibrium now looks like this, or unequilibrium, non-equilibrium. Because the extra OHs are combining here, taking them out to water, and it's creating a hole right here, or removing kids from the seesaw. Right there. So in order to cause the tilt back to equilibrium, the reaction has to shift to the right. Now we're not at equilibrium in either one of these. And this is where the stress factor applies. And remember, Le Chatelier's principle says the equilibrium will shift away from the stress and form a new equilibrium. And so this will form the new equilibrium after it removes enough of the excess hydroxide by H combining with OH, and off into water it goes. And as it does, it eventually this eventually goes out, and this continues to break down and deliver. That's what I forgot to say. H2CO3 breaks down and delivers more hydrogen, and it continues to deliver hydrogen as long as hydrogen's been taken out of the right side until all the OAC is gone, and here we have a new equilibrium. As this process takes place, the H2CO3 or acetic acid decreases. You have a lower concentration of acetic acid, and you have a higher concentration of acetate ion or conjugate base until you reach a comfortable new hydronium ion concentration in that buffer system. And so whether you're adding acid or whether you're adding base, the chemistry of this equilibrium takes over and shifts the equilibrium from the stress applied back to the stable equilibrium. Now the concentrations have changed, but you still have an equilibrium. Okay, from a quantitative point of view, let's say we take our 50-50 buffer. I call it a 50-50 buffer because it's equal concentrations of acetic acid and acetate ion. We determined earlier that it has a pH of 7.4. Now, we come along in our buffer solution and we add 0.01 molar in hydrochloric acid. So that's going to load up the equilibrium, or apply stress on the equilibrium, such that the equilibrium has to shift to remove the excess hydrochloric acid. So case 1, we want to look at the equilibrium and how it changes. And I'll leave all the aqueous, it's going to be in water anyway. Okay, and initially we have a 0.10 molar, and we have a 0.10 molar in salt or acetate ion, and 1.8 times 10 to the minus 5 molar in hydronium ion. So there we have, and this is going to provide a pH equals 7.4, like that. So here comes the excess acid. Now, the acid will disturb the equilibrium by loading up the right side of our seesaw. So if we look at this as a seesaw kind of issue, a little more straight seesaw right here, then we add more hydronium ion in here. This thing's going to tilt like this, so we're going to have a disturbance on the right side. And so in order to recover a horizontal condition, we have to shift the reaction to the left. That is, the acetate ion is going to have to combine with the hydronium ion and make more acetic acid until we get enough weight on the left side here to bring the balance back horizontal. Now, as we do that, and it's tilted to the right, what's going to happen to the concentration of the acetate ion? Well, it's going to go down in concentration. So we have to decide on this early, so we'll know how to add and subtract the excesses from the equilibrium. So the concentration here is going to go down, and it's going to shift to the left, making the concentration of HOAC increase. So when we're trying to get rid of 0.01 molar HCl, so this is going to take it up. So I have to look at this as a decrease in 0.01 molar, because you're combining the excess acid with the acetate right here. So the acetate's going over here and forming acetic acid, so it's increasing by 0.1 molar. So you're going up here and down here by equal amount. And when that happens, you reestablish the equilibrium. So once the new equilibrium is formed, we now have 0.11 molar in acetic acid, and we now have 0.09 molar in OAC. Now, as a common ion issue, we have to apply the equilibrium expression to calculate what the new hydronium ion concentration is. So we don't know. From Ka, okay, equals the product's H plus concentration, and we're talking about new equilibrium, times the new acetate concentration over the new acetic acid concentration. We can solve this for the hydronium ion concentration, new, and that would be the Ka value, and the Ka value for this is 1.8 times 10 to the minus 5. We'll put that up there. Ka value times the acetic acid concentration divided by the salt concentration, like that. And so we come over here and get the new hydronium ion concentration, 1.8 times 10 to the minus 5. We have a new acetic acid concentration, which is 0.11 molar, divided by a 0.09 molar base concentration or acetate concentration. Everything's going to finish in moles per liter. And this gives us 2.2 times 10 to the minus 5 mole per liter in hydronium ion, which is in our new equilibrium. So with that, we want to calculate the new pH, which is minus log of the hydronium ion concentration, which is minus log of 2.2 times 10 to the minus 5 mole per liter, which gives us 4.65. This is the new pH. Okay, I realized I wrote down the wrong pHs for the buffer system. I don't know where I got them. Anyway, the buffer system should have had a 0.1.1. We started with a 4.74 pH, and after the buffer system had removed the excess hydronium ion, we went from 4.74 to 4.65. We'd measured a 0.01 molar hydrochloric acid system, you would have probably a 2 pH. That's an extreme change. It's almost to the bottom of the pH scale. But here, the change was extremely small. Now, one thing I want you to notice, and we can do this with the excess, say, sodium hydroxide, when you add an acid to a buffer system, it's going to shift the pH in an acidic direction. If you add a base to a pH buffered system, it will shift the pH toward the basic range. Okay, now let's look at adding an excess of hydroxide to the same 50-50 buffer system. See if I can remember to put the 4.74 in the right place this time. Okay, so what's happening in our system, HOAC, still ionizes to the hydronium ion, the acetate ion. And if we start with a 50-50 buffer, this system will have, again, a pH of 4.74. This is what the actual value is. Okay, so when we add the OH, what's going to happen? So the OH has got to be, excess OH has got to be removed. So we're going to add an excess of OH, and so we're going to 0.10 molar extra hydroxides in this. Well, the only thing that's going to take that hydroxide out is the hydrogen, hydronium ion, hydrogen reacting with the OH to form water. So H is going to react with OH and it's going to produce H2O. Well, that's going to reduce the concentration here until it completely eliminates the excess OH. So at the same time as it goes out, this is going to decompose and send more hydrogen, and it's going to continue to send hydrogen as long as there's an excess of OH or enough that would disturb the stable equilibrium. Well, anyway, this is the initial condition, change in the conditions and change of our new equilibrium. And so if this is going to be the one that's taken down, the seesaw is going to tilt to the left. And it's going to have to shift to the right by decomposition of the acetic acid to make more hydrogen to continue to react with the OH and ultimately remove all the excess and reestablish a new equilibrium. So in the process, we're going to see the concentration of the acetic acid going down with the concentration of acetate going up by an amount equal to the 0.01 that we had to remove. So this goes down by 0.01 molar, leaving us 0.09 molar at the new equilibrium. And this one increases because it's shifting to the right, and 0.01 molar, and at equilibrium is 0.11 molar of conjugate base. Now, of course, this will, when you reach the proper concentrations, establish a new hydronium ion concentration, which we calculate in the same way we calculated the hydronium ion concentration when we added the excess acid. So here is Ka to again equal hydronium ion, acetate ion, and acetic acid structure, and solve for hydronium ion. I like to do it like this. We use the Anderson-Hasselbalch equation if you want to. I don't care. So this is Ka times the acetic acid and salt right here. So the new hydronium ion concentration is equal to 1.8 times 10 to the minus 5. The acetic acid is 0.09 molar now, and 0.11 molar for the salt. And so we wind up with 1.47 times 10 to the minus 5 in the new equilibrium. So the pH now new is equal to minus log of the hydronium ion concentration, which is equal to minus log of 1.47 times 10 to the minus 5, and that's equal to 4.83. Well, we started with a 4.74, and as I indicated earlier, you throw a base in, the equilibrium will shift to absorb that base, but it will also shift the pH in that particular direction. Okay, now with foundation in chemistry a little bit of how buffer systems function, we've learned that if you apply a stress to an equilibrium is stable, the reaction will take over and shift away to eliminate stress, away from the stress. Now, I describe this issue in the same way I basically described the acetic acid buffer system. So let's put this on a seesaw also and see what happens if we disturb the equilibrium. Now, what factors will disturb the equilibrium of the bicarbonate and carbonic acid equilibrium? Well, as I understand it, it's all about gaining and losing carbon dioxide. Carbon dioxide is a waste product in the biological systems. We inhale carbon dioxide and we exhale carbon dioxide. We take in oxygen, oxygen exchange takes place in our body and converts to CO2 and spits out CO2, and then we do it again, and we keep drawing that back in and out. Well, as long as everything's normal, this seesaw will remain in that capacity, and we'll have a balanced concentration of CO2 water. And if we build up too much CO2 and we have a little bit of tilt this way, well, that'll combine, form this. Carbonic acid will break down and form some hydronium ions and bicarbonate, bring your equilibrium back, and and vice versa. So this seesaw is constantly tilting back and forth under normal conditions. It will be the rate of the forward reaction is equal to the rate of the reverse reaction, and so we don't experience any major discomfort relative to pH changes. So our body automatically adjusts itself. Now the normal range, as I understand it, runs about 7.35 to 7.45. I think that's the common representation that I've seen in all the books and videos I've looked at. So if we get outside of that pH range, it becomes basic or becomes acid. We start calling it acidosis. If it's situation pH gets down in here, we call it acidosis, and if the pH shifts on up here, we call it alkalosis, as I understand it. Again, disclaimer, I'm not a medical doctor. I'm just telling you how I describe and see this equilibrium shifting if a stress is applied. Okay? Now, to begin with, the system is controlled by our biological processes. One is our respiratory system, and many of the presentations that I've seen apply the respiratory to this CO2 H2O. So the stress factors that will disturb CO2 and H2O are typically respiratory. And on the hydronium ion bicarbonate side, the factors that will apply stress to the right side come from metabolic effects. Down there. So let's look at the respiratory effects. It's all about getting rid of the CO2. Well, the bad things that can happen is one, you get rid of too much CO2. Okay? Excess loss of CO2 without replacing it, or two, excessive buildup of CO2. Now, as I understand it, an excessive or rapid loss of CO2 can occur if you enter a condition known as hyperventilation. Hyperventilation is being a fear factor, is what I call it, and you get scared and you are breathing real fast and exhale all of the CO2, and you reach a point at which you can't exhale anymore CO2. You got rid of too much CO2. And if you have a condition that would result in the buildup of CO2, that's in one capacity respiratory failure. So we can say respiratory failure. Well, if case one, we build up an excess of CO2 and the respiratory effect, that's going to load up the CO2 on this side, and that's going to cause your seesaw to tilt down like this. Excessive loss, excuse me. You lose a lot, that's going to create a hole here, sorry. And it's going to cause your seesaw to go like that, okay? And you're going to find that the carbonate and hydronium ion is going to shift into carbonic acid, and then the carbonic acid is going to break down to replace the lost CO2. And that's the chemical mechanism that would be taking place. The chemistry of our body doesn't stop. Your lungs may stop, but chemistry doesn't. Breathe in the bag is another fix, quick fix on the respiratory issue relative to hyperventilation and so forth. So in the case of loss of CO2, okay, let's look at an excessive loss of CO2 and see what effect it has on this equilibrium. Now, hyperventilation, an excessive loss of CO2, this part of the seesaw, if you would, loses weight and would cause the shift in, as you see it, like this. So now the equilibrium has to reestablish itself. It's no longer at equilibrium. So now the process has to shift to replace the CO2. And as a result, you have hydronium ions and bicarbonate ion concentrations decreasing to make carbonic acid, which breaks down to replace the lost CO2. Now, this is the chemical process we're talking about here. So without breathing in and blowing in the bag and replacing CO2 very quickly, bringing it back down, essentially you will see a decrease in the hydronium ion concentration, because this has to combine to break the carbonic acid, which decomposes to reduce the CO2. Well, that's a decrease in hydronium ion. Well, that also increases the pH, and that goes toward the basic range. And as a result, we're looking at alkalosis in that capacity. Now let's look at excessive retention of CO2, or CO2 building up in the body as a result of respiratory failure. Probably the most extreme example would be heart failure, in which the body does not continue to breathe. So if we have an excessive retention of CO2, we would look at that in the worst case scenario. And I'm not a doctor. I'm not trying to teach or prescribe anything. Respiratory failure. As a result of respiratory failure, you're not exhaling or delivering or releasing any CO2. So that's going to build up an excess of CO2 on our equilibrium seesaw, and it's going to make it heavy on this left side. So we got to get rid of this stuff somehow. Well, the lungs aren't working, so what do we have to do? Well, the little help you're going to get is going to result from the shifting of the equilibrium. CO2 is going to react excess. It's going to react with what water you have, and it's going to form some carbonic acid, and it's going to break down very quickly into increasing the hydronium ion bicarbonate. So as a result, you fail to exhale the O2. But one of the things, the O2 metabolism continues, and you'll build up some CO2. The equilibrium then is tilted left, or toward the CO2 side, and is forced to shift away from the CO2 side of the equilibrium. As a result, you're building up larger hydronium ion concentration in the system, which is a decrease in pH, and that goes toward the acetic end, or resulting in acidosis. Well, what's the fix? Okay, well, you got to kickstart the breathing again. So how you do that? Okay, defibrillators, CPR. So it's an extreme issue. So this is my general interpretation of the respiratory effects on the bicarb carbonic acid. Now, in the metabolic effects on the bicarbonate carbonic acid system, we look to the carbonate hydronium ion side of the equilibrium and recognize that problems or stresses are applied when we have too much acid buildup, or we can't get rid of the acid in the system, or we're not making enough acid in the system. And as a result, the kidneys would probably would be shutting down, and you would have renal failure. And so we're not able to pass the excess acid in the system. So you start building up an excess acid and you go into severe acidosis. In this case, you get a little help by a shift back toward the H2CO3 side, in which breathing can remove some of the acid, but if you have renal failure, you're not going to be quick enough to, you're not going to breathe out enough CO2 to cause enough shift of equilibrium to unload this excess hydrogen. So what we're essentially talking about here is, so the metabolic pathway would have involved the kidneys, which function to dialysis of the blood system. And if you have kidney failure, renal failure, you can't remove the excess hydronium ions, which loads up the equilibrium on the ionized side, the hydronium ion bicarbonate side, and forces the equilibrium back to the left. Well, if you should have some help from the kidneys to remove the excess acid, but if you don't have that, the biological equilibrium here is not going to be fast enough to protect you, and you're going to have to go into acidosis shock or have some dialysis done. So anyway, that's to essentially shift to the left to reestablish the equilibrium. Now finally, we look at the excessive loss of the hydronium ion from the metabolic hydrogen bicarbonate side as a result of extreme dehydration. And this is, of course, excessive fluid loss by whatever mechanism, over a hot day, or running on a marathon, or just like to sweat. Anyway, so the issue is the equilibrium will lose the hydronium ion from that side of the equilibrium, and you'll create a hole there. As a result, your equilibrium balance will tilt to the CO2 side. And yes, the CO2 H2O will try to replace that, but if you have an extreme dehydration, it's not going to be fast enough to replace that hydronium ion. And as a result of the loss, the kidneys will shut down to keep you from losing water. And the hydronium ion, of course, is already very, very low, and you're trying to shift the CO2 back over here, and it's not replacing the hydronium ion fast enough. You have an increasing pH because of the low hydronium ion, and you wind up in alkalosis, which is a bad thing. Now, in conclusion, please understand that what I've presented is exclusively from a chemistry course standpoint, and I don't intend to make recommendations on any applications of this. All I do is explain what's going on. But to my best knowledge, this is what is happening in the bicarbonate carbonic acid equilibrium, and it's how it's related to the respiratory process and the metabolic processes in disturbing the equilibrium, or the equilibrium taking over and keeping us from overdoing the metabolic or overdoing the respiratory. There's much more to learn about the equilibrium and how it works physiologically, so I encourage you to go online and look up citations and read them. Thank you much for listening.